Hello, everyone. Welcome to PyData Global 2024. I'd like to bring on Brannigan of Row Signal. He will be giving his talk, Build Simple Scalable Data Pipelines with Delta Lake and Polars. Thank you so much for joining us. I'll let you take over.
Hi, I'm Liam. I'm going to talk about how we can build simple and scalable data pipelines with Delta Lake and Polars. So the two key messages I want you to get out of this talk are, one, use Delta Lake to spend less time managing your data, more time getting value from your data. And two, use Delta Lake and Polars to query your data faster. So briefly about me, my background's in physical oceanography, where I did my PhD. I'm currently lead data scientist at Julian, where I build grid-scale battery optimization software around the ideas I'm going to present here. In open source terms, I'm a minor contributor to Polars and Delta Lake, primarily in documentation. I post a lot about data science and social media, so you can find me across all the networks. I have a popular Udemy course on Polars, and I'm launching a new Udemy course on using lakehouses in Python. Now, what are the challenges with managing data? Well, here's our scenario. We're building a machine learning pipeline to forecast electricity prices. This is a production pipeline where we add new data every day, rather than just working with a static data dump. So here's day one. We get the initial data, and it looks like this with a price every 30 minutes. As you can see, we're going to keep the data sets pretty simple in this talk, so we can focus on the concepts. So how do we store this data? To demonstrate the challenges we're going to face, we use a simple approach where we save the data as a CSV in our data directory with the date in the file name. Equivalently, we could save them in cloud storage like S3. Now, in practice, I'd probably use a more sophisticated approach with, say, partitioning, but let's just keep it simple for this purpose. So the next day, we get some more data, and we need to add this to our dataset. So we save it like this in our directory. Now things start to become more challenging. Later, we find out that the first two rows for the second day were incorrect, as they repeated the prices for the first day. So we have to update our dataset with this new data you see here. In this simple scenario, we can do the update by just overwriting the existing CSV for the second day. However, overwriting the file means that we lose the ability to reload earlier versions of the dataset. In addition, it may be the case that we can't just overwrite an entire file, but instead we have to manually figure out exactly which rows were incorrect and overwrite them. That's a bunch of manual work. On the third day, we see that the schema has changed because our data provider has decided to add in a new isHoliday column. To handle this, we now have to rework our pipeline to make sure that it can handle changes in the schema. Even if we don't have data updates or schema changes, after a while, we end up with lots of small files. As time goes on, it'll take longer just to load the dataset because of the sheer number of files, especially if they're saved in cloud storage. It would be great if we could combine these into larger files, but we'd need to do that manually. Now we want to do some exploratory analysis to help our model. We want to dig into electricity usage on holidays. Is it enough just to flag that a day is a holiday? Or does, say, Christmas Day have different patterns of electricity usage than St. Patrick's Day? To investigate this, we write this query with Polars, which in the first row scans all the CSV files, and in the second row looks for all the rows with holidays. Now, Polars is really clever, but to do this, it has to load all the CSVs and search for the holiday rows. Instead, it'd be better if we had metadata which set out which files contain holiday rows. Now you get your pipeline automated, and every day you write new data to the cloud. However, after a couple of weeks, the network connection breaks when the pipeline hasn't quite finished writing the CSV. You save an incomplete file, which then might break your forecasting pipelines. What we need here instead are transactions that guarantee that writing the dataset either works fully or not at all. So that's just some of the challenges we face when managing a live dataset. Already, we're developing a wish list of features that can save us from a lot of manual work to resolve them. Firstly, we want data updates to be straightforward. Then it'd be great to have dataset versioning so we can reload earlier versions. automatic compaction of small files into big ones would help to speed up our queries. And it would also be great to track what is in each file so we can do file skipping in our queries. It would also help to have transaction guarantees so we don't end up with incomplete files. And we want all of this to work locally and on the cloud. So not much to ask, really. So how do we do better than this? Well, I'm proposing a solution built on 3 tools. The first tool is the Parquet file format. Parquet files have some major advantages over CSV files. Firstly, a Parquet file preserves the metadata of each column. So for example, the time column is loaded as a datetime column, and we don't need to parse datetime strings. Secondly, a Parquet file has a structure that allows a smart data frame library like Polars to limit the amount of data it has to read out of a file. The internal structure of a Parquet file is shown in this schematic. The schematic comes from this great data engineering Substack that you see linked there, and thanks to the author Vu for letting me use his image. In this Parquet file, we have 3 columns and 9 rows. Now, Parquet files are divided internally, so we don't have to read the entire file each time. Firstly, the files are divided into row groups. In this picture, there are 3 rows per group, but 300,000 rows per group is more common. Within each row group, the data for each column is stored separately as column chunks. What this structure means is that if our Polars query only needs data from columns A and B in the first row group, then Polars can just read columns A and B from the first row group. So how does Polars know if only data from the first row group is needed? Well, it's because statistics on the range of data in each row group is also stored in the file. A smart data frame library like Polars takes advantage of these statistics when it sees only a limited amount of data is required. The second part of our solution is a lakehouse package. We're going to use DeltaLake as our lakehouse package. So what is a lakehouse? Well, a lakehouse is basically a system for data storage. In a lakehouse system, you don't work with individual files, as we did with the CSVs. Instead, we manage each dataset as a table, and the lakehouse tool then takes care of the underlying files. Our lakehouse then comes with all the tools we wanted in our wish list to manage the data. There are a number of lakehouse tools out there. The best known are Hudi, DeltaLake, and Iceberg. Now be aware there are 2 implementations of DeltaLake. We'll be using the Delta RS version, which is an open source project written in Rust with a Python API, which implements the DeltaLake protocol. This package has no dependence on Spark, Java, or Databricks. The reasons I chose to work with Delta RS are its simplicity, its speed, and how well it integrates with Polars. Just to avoid confusion, note that Delta RS is the name of the project on GitHub, but DeltaLake is the name of the Python package. I'll just call it DeltaLake. The last part of our solution is a smart data frame library, and we're going to use Polars. We can use other tools of DeltaLake, such as Pandas or DuckDB, but I've gone with Polars because Polars is really fast and integrates really well with DeltaLake, as we'll see. Now let's move on to our demo of DeltaLake and Polars, which we'll do in a notebook. So here's your notebook here. We start off with some imports. Firstly, we just have some Python imports that we'll use just to manage the data. And then the key imports are really down here. From DeltaLake, we're going to import Delta table and write DeltaLake. And we're just going to import Polars as PL. We'll start by creating our first Delta table. We're going to recreate the simple example that we used at the start. So we create a data frame DF, and it's got 3 rows with time steps and the prices. Now, the first thing to understand about a Delta table is that it's just a subdirectory on your computer that has some files in it. So if we're going to create a subdirectory, we need a path, and we specify that here. We're going to create the Delta table at the tables subdirectory, and then a subdirectory inside there called PyData. And all of this is going to be referenced by this table there variable. We run that, and we also create a path directory to the same table with the path library. Now, just to tidy things up, I'm going to run this line here, which checks that if that directory already exists, then I delete it. So I get a fresh start each time I run this notebook. So now we're going to create our first Delta table. And we do that using the DeltaLake function, write DeltaLake. and the syntax is pretty straightforward. The first argument is just a path to the directory, so that's table dir, and then the second argument is just the data. In this case, it's our Polars data frame, df. And if we run that, we've created our first delta table. Now let's see what that means in practice. And I think you'll find that it's actually simpler than you might anticipate. So what does a delta table look like on disk or in the cloud? Well, we can see that by running ls to list the contents of the PyData directory. I've run that and I get a warning, run it again. So firstly, there's two things here in this directory. First, we have this path here, which is a path to a Parquet file. The Parquet file is what holds the data that was in the data frame. Secondly, we have another subdirectory within PyData called DeltaLog. This is the delta table transaction log. This is where the metadata about that transaction is stored. And that data is stored in simple JSON files. And in this first JSON file, for example, it would show the time this table was created, the operation we did, which in this case was creating a table, and things like statistics on what the range of data was in that in the Parquet file added to the table. So that's all the delta table is. It's just a subdirectory with some Parquet and some JSON files. There's nothing more complicated than that. Now we'll continue and we'll append some data to the delta table. So now we create our second day of data, and this is the second day of data with these incorrect prices, which are just carried over from the first day. Now before, when we wrote data to the table, we used the write DeltaLake method from the DeltaLake library. However, now we see how the Polars integration works, because instead we're going to take our Polars data frame df and call write delta. So this is a method on a Polars data frame, but which writes to a delta table. The first argument to write delta is the directory of the table, so table dir again, and then we specify the mode. So in this case, we're not going to overwrite data, we're not going to create a table, we're going to append data, so we set mode equals append. If we do that, the data that was in df has now been appended to the delta table. We can list what's in the directory to keep track of what's happening underneath the hood with the files. And we see that there are now two Parquet files. One of these came from the first transaction when we created the table, and the second comes from the second transaction where we appended data to the table. And of course, in the delta log, we now have a new JSON file which records the metadata of this append operation. So far, we're just actually writing data to the table, but there's also a lot of values from actually using the delta table object. So we're going to use that here, and we're going to create the delta table object as a variable dt. So to do this, we take the DeltaLake delta table object, and we pass the path to the table. And if we run that, we see here that we get a delta table. Now this delta table object contains lots of metadata about what's in the table. For example, if we call dt.files, we can see the path, we can see which Parquet files are currently referenced by the table. We can also get the schema of the table, and I prefer to call to PyArrow to get it in the simpler PyArrow format. So this tells us in this simple scenario that the schema of our delta table has a time column, which is a timestamp, and a price, which is a float. If we actually just want to read that delta table back into a data frame, that's pretty simple because we can use Polars read delta method. And in this case, we pass it the delta table itself. And if we call that, Polars reads in the delta table back into a data frame. So that's how quickly we can load our data back in and how simple it is to load our data back in from the table into a data frame. Now we're going to do the more tricky operation where we have this corrected data and we want to overwrite the incorrect values with the updated data that we get, which is correct. So that updated data is going to be in this data frame here called update.df. And we can see here that we have the timestamps with the updated data and then the prices over here that we want to overwrite the existing values with. Now before we did an append operation, and an append operation, you just add all of this new data to the delta table. But if we did that in this case, we'd end up with duplication because we'd have the existing values at midnight and half past midnight, and we would have these new values. Instead, we want to do what's called a merge in DeltaLake. In a merge, we compare the new data to the existing data in the table, And then when we find a match between them, we do some kind of operation, which might be, say, inserting data, it might be updating the data, or it might be deleting data. And we'll see the syntax for that here. The first key step in this merge operation is to compare the new data. And to do that, we need to specify the condition that we're using to compare the new data to the existing data. And we do that here in this predicate. We specify the predicate with this SQL-like string. And the predicate is like this. We're looking for time steps that have the same time in the existing data, which is called target, and the new data, which we call source. We're also looking for rows where the price doesn't match. And so we specify that as target.price. So the existing price data is not equal to the new price data. When we find this predicate is met, then we want to do something to that row. We see how we actually implement that here. So we start here with our new data frame, update df, which has the data we want to add to the table. We call write delta, just as we did before, to add data. And of course, as always, we pass the path to the delta table. Now, in this case, the mode is equal to merge, because we're going to do some kind of comparison operation and merge this data in. And then we pass delta merge options, which tells Polars and DeltaLake how the comparison between the new data and the old data should be done. But we still haven't told them what we want to do when it finds a match between the new data and the old data. So we do that by passing down here dot when matched update all, which means that when this predicate is satisfied, the DeltaLake will update the data with the new corrected data over the existing incorrect data. Finally, we call execute here, and that actually triggers DeltaLake to do the transaction and do this update on the dataset. Just be aware there's something clever happening here. So update df is a Polars data frame. Write delta is a method on a Polars data frame, and we pass all these arguments here. However, when matched update all is actually a method of DeltaLake, and so is execute as a method of DeltaLake. So the reason we can do that is that when we do update df and call write delta on a Polars data frame, the output is actually a DeltaLake table merger object. And that means that we can continue this Polars code here. Because the output is a DeltaLake object, we can then call the DeltaLake methods to enforce the fact that we want to do this update operation. Now, that's about as complicated as the syntax will get with DeltaLake. So I appreciate that's a lot to take in first effort. But if you were to compare what this would be like to do manually, I can assure you that this is a lot simpler than managing this operation yourself. So I'll execute this cell here and this cell here. And then DeltaLake provides a summary of what's happened in the delta table. The key point here, we see that we have number of target rows updated to. So DeltaLake detected that there were 2 overlapping rows with the existing data and updated those rows with the new price. If we read in the table, we can see that for these first 2 rows here, we now have the corrected price in the current version of the table. So in this case here, we've used merge to update values. However, we can also use it to insert a row if it doesn't exist. We can do upserts, where we update existing values and insert new rows, or we can use it to do deletes. If we look at what's happening in the delta table directory, we can see that we now have 3 Parquet files. However, if we create the delta table, an updated version of it here, and call dt.files, we can see that there are only 2 Parquet files listed here. So what's happened is that although there are 3 files in the directory, only 2 of these are currently referenced by the delta table. So one of these is an old Parquet file, which is there if in case we want to time travel back to an earlier version of the dataset. So it hasn't been deleted, but it's no longer referenced by the table because DeltaLake has observed that we needed to overwrite that file or to overwrite the values in that file in order to update the dataset. We can also handle schema evolution. So for example, we now have schema df with our is holiday column, and we can write this into the delta table. So we have schema df, our new data. We call write delta again, the path to the delta table. We want to append this data. However, this time we're going to tell DeltaLake that it's okay for us to update the schema. Even though this has new columns, it's still okay to add that to the table. If we do that, we've appended that data. And if you read the updated table, we can see that we now have the is holiday column and that we have null values down here for the records where we didn't have this column. so we can handle the schema evolution. As I mentioned above, we've now got multiple different versions of this delta table. So we can see that here by recreating our delta table object, and this time we're going to call dt.version. If you run that, we see that we're now on version 3 of the table. So we created it, did an append, did an update, and then did another append. So we're in version 3. If, however, we felt that we made a mistake and we actually wanted to reload an earlier version of the table, we can do that here by calling pl.readDelta and passing version equals 2. If we found that we'd really made a mistake and actually want to move the state of the table back to an earlier version, we can do that with this method on a delta table, so dt, and we call the restore method, and then we set here target equals 2, and that tells DeltaLake to restore the state of the table back to its state at version 2, which I'm not going to call at this point. We now think about optimizing small files. So if we recreate our delta table again and look at the number of files, we see that we now have 3 small Parquet files. What we want to do is to compact these into one larger file. And we do that here by calling dt, which is our delta table again, optimize.compact. If we run that, we again get a summary from DeltaLake, and it says number of files added 1, number of files removed 3. And if we list the files, we see that the current table now just has a single Parquet file. So it's done this compaction of small files to big files for us. If we list the contents of the directory, we can see that we now still have the old Parquet files in case you want to time travel back to those, but these ones down here are no longer referenced by the table. If at some point we decided we did actually want to delete them, then we can use the delta table vacuum method, and that would actually go about and delete any of the older files older than 24 hours. So now the last thing I want to talk about is how Polars the integration with Polars in terms of doing query optimizations. So we've seen before that we can use pl.readDelta, and that reads in the entire delta table. We can also do lazy queries with Polars. So in this case, we do pl.scanDelta, and in this case, we'll just call collect, and that will evaluate the query, which is the same thing here of just reading the entire table. There are 2 key query optimizations Polars does with the delta table. The first is called projection pushdown optimization. We see an example of that here. We do pl.scanDelta to start a lazy query. We do a group by on the time column and an aggregation on the price column. So we're only using 2 out of the 3 columns for this query. If we call explain here, instead of running the query, Polars prints the optimized query plan. And at the bottom of the optimized query plan here, we see it says project 2 out of 3 columns. That means Polars detects that only 2 out of the 3 columns are needed for this query. So when it loads the data from the delta table, it will only read 2 out of the 3 columns using the Parquet structure that we saw earlier. The other key optimization is what's called predicate pushdown optimization. Again, here we have a lazy query with scanDelta. And this time we're going to do a filter operation. So filter means we're only going to look for the rows where isHoliday is equal to 0. We call collect to evaluate that. And what Polars will do in this case is that it will look at all the Parquet files in the delta table, and then it will look at all the row groups within the Parquet files to try to see which ones have rows that match this condition. This can be a big time saver if you're loading a subset of a data set, especially from remote or cloud storage. I'm not going to talk much about partition data sets, but I have just actually developed a partition data set with this query here, which takes UK power demand and interpolates it to a 5-minute interval. So I've written this data frame here, which has these date time and power demand columns and so on. And I've written it to S3 to this bucket. In order to make this a partition data set, I've said partition by year, and then some storage options for writing to S3. If I want to query that delta table in the cloud, all I have to do in this case is pl.scanDelta. Then this is the path to the bucket on S3, some storage options to tell it where to find that bucket. And in this case, note that I've done filter pl.callYear is equal to 2009. So with a partition data set like this, we have further subdirectories where each subdirectory corresponds to a year. So in the case of this, Polars will look at this query and it will detect that it only needs to look in one of the subdirectories for 2009 and do a lot of file skipping to minimize the amount of data it has to transfer across the network and back to my machine. So if I run that, I will get an AWS error because I've just set my credentials up wrong, but that's the way it works in terms of how easy it is to query from the cloud. So now I'm going to wrap up. So the first takeaway is that managing data by yourself is really hard. So I've found that I've got much more power from using DeltaLake and Polars because it gives me all this functionality to do append, overwrite, updates, inserts. It allows me to time travel to different versions of the dataset, gives me ACID transactions and file skipping. I recommend you try it, and it's really simple. All you need to do is pip install DeltaLake and Polars. And I really encourage you to engage with these projects. There's really great communities, so check out the Polars Discord or the DeltaLake Slack. Connect with me on social media. I'd love to hear from anyone. And above all, thanks to the open source developers who actually brought us these packages. Okay, thank you very much. So there's one question here. So someone's asking if they'll be able to get the notebook as well. Yes, I can put the notebook in the resources. And there's a question saying, how mature is Delta RS compared to Delta Table from Databricks? Well, for me, I know that I've been using this project in production for 6 months and that all the core functionality is there. And that I think that it's not quite as fully featured as Delta Table on Databricks, but in practice, all of the kind of things you really need to get value from this are in the project already. Happy to hear any more questions in the minute or two we got left. Here's a good question. How easy is it to incorporate highly parallel workflows with DeltaLake? So one advantage of having many small Parquet files is that you can write a partition in parallel and then read a partition and it's all good. Will DeltaLake prevent this? There are some complications here because one thing depends where you're storing the data. If you're storing data on S3, that you can't do parallel writers or this kind of parallel operation at the moment. But that's also because S3 was missing some features, which have actually only been added in the last week or two. So I think that at the moment, it's a bit limited in terms of really getting the full parallel workflows, but then this is actually developing really quickly in terms of what the storage offers you. The other aspect is that when Polars queries this kind of set of Parquet files, that it actually does a lot of parallelization itself. For example, if you've got a really one big Parquet file, Polars will read that in parallel and read lots of either columns in parallel or read lots of row groups in parallel, so that there is a lot of parallelization happening underneath the hood.
All right, Liam, thank you so much, and thank everyone else who joined. Please continue the discussion in our Discord server, and you all have a great day. Thanks again.
Thank you very much.